Imagine you step outside on a clear morning. The air is cool, the light is warm on your skin, and somewhere above you, 150 million kilometers away, something is happening that you cannot see, cannot feel, and cannot stop. A bubble of magnetized plasma, the size of a continent, just tore free from the surface of a star. It is accelerating, right now, silently, through empty space, carrying the energy of 1 billion nuclear weapons, all aimed in one direction. You don't know it yet. Your phone still works. The power is still on. The satellites above your head are still transmitting. Everything feels normal. And that is exactly the problem. Because the star we call the sun, the one that feels warm and familiar and safe, is not what it appears to be. It is not a steady flame. It is not a fixed light in the sky. It is a living, breathing, magnetically violent system that has been building towards something for the last 11 years. And we are only now, with machines flying through its atmosphere for the first time in human history, beginning to understand what it is truly capable of. Stay with me. From a distance, the sun looks almost boring. A pale yellow sphere, steady, unchanging, the same as it was yesterday, the day before, and the day before that. You could observe it for your entire life and never see it do anything dramatic. By astronomical standards, it is a perfectly ordinary star, a G-type main sequence star, one of roughly 100 billion in the Milky Way alone. Medium size, medium temperature, medium age. Scientists sometimes call it unremarkable. It sits 150 million kilometers from Earth, close enough to warm our oceans, far enough to feel unthreatening. Its diameter spans 1.4 million kilometers, 109 times wider than our entire planet. But at that distance, it fits behind your thumbnail. So it looks small. It looks stable. It looks like something you can safely ignore. But that appearance, the lie. Humans have been watching the sun for thousands of years, but we only began to understand what it actually is relatively recently. On the morning of September 1st, 1859, a British amateur astronomer named Richard Carrington was sketching sunspots through a darkened telescope lens. Then something extraordinary happened. A blinding flash of white light erupted from the sunspot group he was studying. It lasted about 5 minutes and then vanished. Carrington suspected it was significant, but he wasn't certain. He wrote in his notes that one swallow does not make a summer. 17 hours later, the entire night sky caught fire. Auroras blazed as far south as Cuba, Panama, Colombia. Gold miners in the Rocky Mountains woke up at 1 a.m, made breakfast, convinced the sun had already risen on a cloudy day. In Boston and Portland, telegraph operators noticed something impossible. Their machines were sending and receiving messages with the batteries completely disconnected. The aurora itself was powering the wires. And then the wires caught fire. That event, what we now call the Carrington Event, was the first documented proof that the sun could reach across 150 million kilometers of empty space and directly, physically touch the surface of our planet. Not with light, not with warmth, with something else entirely. Something that would take another century to properly name and understand. Let's start with what's actually happening inside the sun. Because once you understand the machinery, the scale of the danger becomes much clearer. Every single second, the sun fuses approximately 700 million tons of hydrogen into helium. That process, nuclear fusion, converts mass directly into energy. And in that conversion, roughly 5 million tons of mass simply disappear, transformed into pure energy. Every second, without stopping, for 4.6 billion years. To put that in perspective, 5 million tons is approximately the combined weight of every commercial aircraft currently in flight on Earth, multiplied by 1,000, vanishing as light and heat every second. The core where this happens sits at roughly 15 million degrees Celsius. The pressure there is 250 billion times the pressure at Earth's surface. Under those conditions, matter doesn't behave like matter anymore. It becomes plasma, a state in which electrons are stripped violently from their atoms, and everything moves at speeds that break intuition. But here's something almost no one thinks about. The photon of light born from fusion in the sun's core right now will not reach the surface for somewhere between 10,000 and 170,000 years. The interior is so dense, so impossibly packed, that light itself gets trapped, absorbed by particles, re-emitted in random directions, zigzagging outward through layers of plasma for longer than anatomically modern humans have existed on Earth. The light warming your face right now left the sun's surface 8 minutes ago, but it was born in the core during an era that predates the last ice age. The sun we see is not the sun that exists. Now, here is where the sun stops making sense. The visible surface of the sun, the photosphere, sits at about 5,500 degrees Celsius, devastating, incinerating, hot enough to vaporize any material known to science. But as you move away from that surface, upward into the atmosphere, the temperature should drop. That is how heat works in every context we understand. Move away from a fire, feel cooler. Fundamental physics, unbreakable law. Except the sun does not follow this rule. About 2,000 kilometers above the photosphere, you enter the corona, the sun's outer atmosphere. And there, instead of cooling, the temperature erupts. It climbs to somewhere between 1 million and 3 million degrees Celsius. During active events, it can spike above 40 million. The sun's atmosphere is between 200 and 7,000 times hotter than its own surface. Scientists have known about this since 1939, when a Swedish physicist studying the corona during a solar eclipse identified a spectral emission that could only be produced by iron heated to impossible temperatures. The scientific community at first assumed it must be a brand new element. They called it coronium, convinced no known substance could behave this way. It took decades of refined quantum theory before they realized it was just ordinary iron. Ordinary iron, twisted into a state that should not be possible at that distance from the energy source. That discovery launched what researchers now call the coronal heating problem, an unsolved mystery that has persisted for 86 years. Two leading theories exist. One involves Alfvén waves, magnetic oscillations that propagate from the surface into the corona, carrying energy upward and depositing it as heat. The other involves magnetic reconnection, where field lines in the corona become knotted and strained beyond their limit, then snap explosively in microscopic bursts called nanoflares. In October 2024, a team at Princeton Plasma Physics Laboratory published a study demonstrating Alfvén wave reflection behavior in a laboratory plasma column, a significant step toward finally understanding the mechanism. But a step toward understanding is not understanding. The atmosphere of our own star still defies the most basic principle of thermodynamics, and we still do not know why. And here is what makes that unsettling beyond the physics alone. That impossibly hot corona is where the sun's most dangerous behavior is born. The corona is not static. It pulses, it flows, it releases material into space continuously, a constant stream of charged particles, electrons, protons, helium ions, moving outward in all directions at between 400 and 800 kilometers per second. This is the solar wind. It fills the entire solar system. It stretches past Pluto. It shapes the space environment of every planet in our neighborhood. On Earth, we are protected by our magnetic field. It deflects most of the solar wind around us, compressing on the sunward side, drawing into a long trailing tail on the other. Without that invisible shield, Earth's atmosphere would erode over millions of years, the same way Mars lost most of its atmosphere after its own core cooled. Its magnetic field faded, and the solar wind began to strip it directly. But the solar wind is just the baseline. the everyday. What makes the sun truly unpredictable are the eruptions that ride on top of it. When magnetic field lines in the corona become sufficiently stressed and tangled, they can rupture. The release is called a solar flare, a burst of radiation traveling at the speed of light. That radiation reaches Earth in exactly 8 minutes. It ionizes the upper atmosphere and causes immediate radio blackouts across the entire sunlit face of the planet, without warning, without a countdown. And often, following directly behind it, comes something far larger. A coronal mass ejection, 1 billion tons, sometimes more, of magnetized plasma torn from the sun and hurled into space. Not a wave, not a ripple, a projectile, moving at speeds between 900,000 and 10 million kilometers per hour. Invisible, enormous, and, in the worst cases, aimed directly at us. In 2024, the sun launched over 50 X-class solar flares, the most powerful category. In May of that year, a sequence of coronal mass ejections arrived at Earth in rapid succession, triggering a G5 geomagnetic storm, the strongest in more than 20 years. Auroras were visible from Puerto Rico, from northern Mexico, from latitudes that hadn't seen them in generations. In November 2025, an X5.1 flare sent a CME toward Earth at approximately 6.7 million kilometers per hour. The resulting storm reached G4. Severe radio blackouts knocked out high-frequency communications across Africa and Europe simultaneously. Power grid operators around the world watched their monitors with the particular attention of people who know exactly how thin the margin is. This was not an exceptional week. This is the sun on an active Tuesday. Go back to 1859. The Carrington CME covered 150 million kilometers in 17.6 hours. A typical CME takes several days. This one arrived before most people even knew to look. The induced electrical currents surging through telegraph wires were powerful enough to physically shock the operators, to ignite paper, to allow transmission with the power completely cut. The aurora itself became the power source. That was 1859. The only technology at meaningful risk was the telegraph. Now imagine the same event today. A Carrington-level CME arrives at Earth. The geomagnetically induced currents surge through the modern power grid. High-voltage transformers, components that take months or years to manufacture and cannot be quickly replaced, begin to overheat. Circuit breakers trip. The grid fails. Not like the Quebec blackout of 1989, which knocked out power for 5 million people for 9 hours. Like something longer. Something that cascades across interconnected systems before anyone can isolate the damage. Satellites in low Earth orbit have their circuit boards burned out. GPS goes dark. Navigation fails. Communications satellites stop transmitting. Internet infrastructure dependent on those systems goes offline. Anything with automated electronic functions begins to fail. Researchers studying this scenario have estimated the economic damage could reach into the trillions of dollars globally within the first weeks alone. The cascading failures across interconnected systems, the kind of damage no single emergency protocol was designed to address, represent a category of risk that most modern infrastructure was never built to survive. And here is what transforms this from a theoretical concern into something more immediate. On July 23, 2012, a coronal mass ejection of Carrington-class magnitude erupted from the sun. Scientists who analyzed it in the years that followed described it as comparable in intensity to the 1859 event, possibly exceeding it. The plasma and magnetic fields involved were among the most extreme ever recorded by modern instruments. It missed Earth by 9 days. 9 days earlier in our orbital position around the sun, and it would have struck us directly. We would have had no meaningful warning, no coordinated response, no plan designed for that scale. We did not know it was coming. and we did not know it had passed until it was already gone. In December 2024, something changed. NASA's Parker Solar Probe, launched in 2018 with a single defining mission: to fly through the sun's corona and observe our star from inside, completed the closest approach to the solar surface ever achieved by a human-made object. On December 24th, Christmas Eve, the spacecraft passed just 6.1 million kilometers from the solar surface, moving at 690,000 kilometers per hour. The fastest any object built by humans has ever traveled. At that distance, Parker flew directly through a coronal mass ejection as it erupted. From inside, the images returned by the spacecraft's wide-field camera revealed something that scientists had suspected but never confirmed with this precision. After a CME erupts, not all of the ejected material escapes the sun. Some of it, in elongated blobs of plasma, falls back. The magnetic field lines stretch, reconfigure, and material rains back toward the solar surface in features scientists call inflows. We've previously seen hints that material can fall back into the sun this way, said Noura Wafi, Parker Solar Probe project scientist at Johns Hopkins Applied Physics Laboratory. But to see it with this clarity is amazing. This is not a minor detail. It means the sun's eruptions are not isolated events. Each CME changes the shape of the magnetic environment it leaves behind, which influences the conditions for the next eruption, which alters the environment again. The sun's explosions have memory. They respond to each other. They are part of a system, more interconnected, more self-referential than our previous models assumed. Which means our models of space weather forecasting, as far as they have come, may still be missing something fundamental. The sun is currently in an active phase of solar cycle 25, a cycle that began in 2019 and has already exceeded historical activity projections. More X-class flares than predicted, more major geomagnetic storms, more CMEs at exceptional speeds. Scientists at NOAA's Space Weather Prediction Center monitor solar output continuously, watching for the magnetic signatures that precede eruptions, building models that might one day give us hours of warning before an impact. The challenge is the final variable, the magnetic orientation of a CME. The single factor that most determines how severely it will interact with Earth's field cannot be measured until the CME actually arrives at monitoring satellites positioned between Earth and the Sun. Their forecasters get somewhere between 15 minutes and an hour of confirmed warning before impact. For a civilization running on electricity, 15 minutes is not very much time. If Parker's ongoing observations help us understand the conditions that produce CMEs before they erupt, if the inflow data helps us model the sun's magnetic recycling with greater accuracy, that window could grow. The answer to one of the most dangerous questions in planetary risk may be sitting in data that hasn't finished transmitting yet. We tend to think of the sun as a given. It rises, it warms, it sets. It has done this every single day of every human life ever lived. It is the oldest constant in our existence, the axis around which every calendar, every harvest, every myth and religion and sense of time has been organized since our species first looked upward. But we now know it is none of those things. It is a 4.6 billion year old nuclear reactor, whose atmosphere breaks the laws of thermodynamics in ways we still cannot explain, whose magnetic field stores energy in configurations that occasionally rupture without warning, whose eruptions can cross 150 million kilometers of empty space and destroy every satellite, every grid, every transmitter our civilization has ever built. Simultaneously. In one generation, our generation is the first in all of human history to have actually flown a machine through its atmosphere, to have watched the corona from the inside, to have seen, in real images from real instruments, the material of our own star fall back into itself after an explosion. We are learning things about the sun that no human being has ever known. And yet, somewhere in the data is still transmitting back from Parker Solar Probe. There's almost Certainly something we have not yet seen. Something the sun has been doing quietly for billions of years, long before there were planets, long before there was Earth, long before there was anyone standing outside on a clear morning, feeling the warmth on their skin and calling it safe. The sun will erupt again. That is not in question. The question is simpler and more uncomfortable than that. On July 23, 2012, the margin between our civilization and a Carrington-class catastrophe was 9 days. How wide is that margin right now? I hope this gave you a new perspective on the star we share our solar system with. If you enjoyed it, consider subscribing. I'll see you in the next one.